Greetings, fellow learners. In this video, we are going to talk about Fast RCNN, the what, the why, and the how. So to set the stage here, a traditional object detection pipeline is going to take an image and then it will localize objects of interest by drawing a bounding box around it, and it will also add a classification label to identify what this object that is localized is. And in 2014, RCNN was the state-of-the-art for such object detection. And in fact, it was one of the first successful attempts at using a convolution neural network in an object detection pipeline. So what is RCNN? Well, at a very high level, RCNN is regions with CNN features, and it was structured in 3 stages. So first, we have an input image. Then to this image in stage 1, we will create region proposals. These are like some 2,000 bounding boxes on areas where an object of interest could be present. Then for each region proposal, we are going to warp it, that is like stretch it out, such that it is of 224 cross 224 dimensions, which makes it compatible with the then state-of-the-art architecture of convolution neural networks for object recognition that was AlexNet. We pass it through a CNN, then on the last feed-forward layers, you're going to get a 4,000 dimensional vector that's going to represent the features of this warped region. And then what we're going to do is pass each of these into SVMs to determine the object in each region proposal. So if there's 1,000 objects of potential classification interest, we're going to train 1,000 binary classification SVMs in order to get like a binary response from each of them. And eventually we can reconstruct the object localization plus classification like this. So this is overall like a 3-stage approach. Now, if you want to get to know more details about RCNN, I'll encourage you to watch my previous video on RCNN first before coming into this, but I'll try to also add some more color and context to the original RCNN as I explain some like new and improved details of this Fast RCNN. So what's now wrong with the original RCNN approach to object detection? Well, there's 3 main things here. The first is that object detection is a multi-stage process. So basically, we take an image, like we mentioned before, we will generate region proposals, some 2,000 bounding boxes where an object may be present. Then we will warp these regions so that it's compatible with AlexNet, pass it through a convolution neural network, which is AlexNet over here. Then we are going to get this 4,096 dimensional vector over here that corresponds to the features of this warped region. And now what we need to do is we do this for each and every single region. And so what you're going to end up with for a single input image, if we extract features, you're going to get 2,000 vectors, each of 4,000 dimensions. And that will represent one image. You can see that this is about like 8 million numbers, so this could be tens of megabytes just to store information of a single image. And now this can amount to gigabytes of storage of training data. And recall, why we're storing this now from the original RCNN architecture is because we need to now pipe this into SVMs. And so they need to be stored somewhere in between generating the features from the convolution neural network and processing it with SVMs. And that's why we need like gigabytes of storage, which was especially a lot for like 2015 when all of this research was going on. Now, the second issue with RCNN is slow inference. So like we mentioned, let's just say we have this 2,000 bounding boxes for an image, and we are going to warp these region proposals. So this is one region proposal over here. We'll pass it through the entirety of a pre-trained AlexNet. And then in order to get like the features for this warped region, then we do the exact same thing where we take another second warped region, pass it through the entirety of this convolution network to get the features there. Similarly for a third, 4th, and so on for like 2,000 cases. Now, the issue here is that we need to perform this expensive like convolution activation pooling sequence of operations, which is like millions of floating point operations for every single region proposal, which could lead to slower inference. Now, the third issue is potentially performance loss. So when we have this like warped region proposal, the issue is that, well, it's warped. So these are distorted in order to fit the 224x224 architecture requirements of AlexNet, but this can decrease accuracy because it is a distorted image. Now, I've written all those three issues out right over here. So in summary, that's object detection is in multiple stages. This increases complexity and disk space for training. 2 is that there's slow inference because of non-shared expensive convolution operations for region proposals. And the third issue is performance loss potentially due to distorted region proposals. And Fast RCNN now can help address these. So let's see how, by starting with its structure. So essentially the structure of the Fast RCNN uses VGGNet as its base. And the reason for this is by the time that this research was rolling around in like 2014, 2015, VGGNet was the state of the art for object recognition in 2015. That is, given an image, it could classify like what that image overall is. Now, let's take a deeper dive into this VGGNet architecture and then also make some changes to see how the Fast RCNN is different and built on top of it. So here is the VGGNet architecture where we first take an input image of 224x224. We will then pass it through a sequence of convolution, activations, and pooling. And in each case, we get like these tensors that are some non-linear representation and compact representation of the input image signal. And so we do a sequence of like 5 of these convolutions, activations, and pooling blocks. So we have convolution, activation, pooling, convolution, activation, pooling, convolution, activation, pooling. And then on the last pooling block over here, we're going to end up with a 7x7 x 512 dimensional tensor. This is a compact, nonlinear, rich representation of the input image. And now what we do is we flatten this out. And if you multiply these, this will be like 25,000 dimensions. And then we'll pipe it through a sequence of feed-forward layers until we get an output layer where we have like 1,000 dimensions for a 1,000 case object classification. So this is essentially the overall structure of VGGNet, where we make use of like 3x3 convolutions for a deep layer. Now, let's see how Fast RCNN is different. So Fast RCNN will actually make 2 major changes. So first, after the sequence of convolution activations and pooling, and just before, we have like the 5th convolution, the 5th activation, that last max pooling layer that we had, we are going to replace it with something called RoI pooling. And what RoI pooling is going to do is it's going to take a tensor of like, this can be, let's just say, a variable length tensor that represents a region proposal, and it's going to map it to a fixed size tensor of 7x7 x 512. And the reason why we want RoI pooling here is because, like we mentioned before, in the case of RCNN, we used to warp region proposals so that they can be, of a fixed size and they can be passed and trained through the network. In this case, we are not doing any warping of region proposals, which means that region proposals themselves can be of different sizes. So by the time we come to this phase, this will represent a region proposal of, it could be elongated, it could be wide, it could be anything. Hence, I represent it by A cross B. But in order to make sure that it is compatible with the future layers of this network, specifically these feed-forward layers, because we need to define this configuration of 25,000 dimensions, like in PyTorch code, we need to do this beforehand. So we need to know exactly how many neurons this is going to be. And hence, this requires a fixed dimension for every input that comes. And hence, we need this mechanism that transforms a variable dimension tensor to a fixed dimensional tensor so that it is compatible with feed-forward layers. And to solve this, we use RoI pooling. So I hope that helps you understand why we use RoI pooling and how exactly we do this. We will look at the next section, but this is one change that we make from the VGGNet in order to get this fast RCNN. Now, the second change that we make is we used to have just this used to go into a 1000 classification feed-forward layer. We no longer do that. Now we have sibling heads where we make it go to first a 1001 dimensional layer for classification. This is 1000 object classifications along with a background class. So there's 1001 neurons here. You can think of this as a softmax. Then it also goes simultaneously to a 4000 dimensional layer where we have 4 neurons for each object category. There's 1,000 of them, and they will represent the bounding box for object localization. And so this will tell us the bounding box, and this will tell us what that bounding box is exactly. And hence together, they can be used in object detection. So those are the two main changes that we make to the structure. Now that we understood the structure of RCNN, let's now go back to what I mentioned about RoI pooling. So we mentioned that RoI pooling is, it converts the variable size tensor that represents a region proposal to a fixed size tensor that also represents a region proposal. We understood the why behind this, but how mechanically do we hope to do this? So let's look at this with a very simple example. So let's say that a region proposal is going to be represented by a 5x5 tensor that looks like this. And what we want to do is we want to map this to some fixed size tensor. Let's say it's 2x2 in our case. And so what we need to do is we are going to bin this entire 5x5 input into 2x2 bins and perform max pooling. So let's say one of the bins looks like this. Within this, we are going to perform max pooling. The maximum is 0.3, and hence we write it out. The second bin is this, where we write out 0.8, output of max pooling. The third bin could be this, where the output is 0.6, and the fourth bin is this, where the maximum is 0.5. And hence, this is a fixed size tensor that we can then pass through the feed forward layers of the network. So this is one example. Now to hammer home this point of what we're actually trying to achieve here, let's look at another region proposal. Let's say this is the second region proposal, but this time it's a longer one of 2x6 and represented by these numbers over here. So what we need to do now is we want to map this to a fixed size tensor of 2x2. And hence we need to bin this into 2x2 bins in some way. And so we could say that, this would be bin 1, where we're going to take the maximum here, 0.1. Bin 2, it's 0.3. This is bin 3, and hence bin 4. And so this is now a fixed size tensor that is passed through the rest of the network. And so I think you can kind of see this effectively. We can bin any arbitrary tensor of A cross B into a fixed size tensor like 7 cross 7 over here to be compatible with the rest of the network. And hence this RoI pooling, while the mechanics of it is quite simple, it is a very important process in this fast RCNN object detection pipeline. So I hope that makes sense. Now that we understood the what's, the whys, and the hows of the fast RCNN, let's actually walk through the entire training procedure for a fast RCNN object detection pipeline. So what we want to do first is we take a VGG net that is pre-trained on object recognition. So I wrote a pre-trained VGG net architecture. It's basically 5 convolution activation pooling layers. And let's say that this will output eventually like a 7 by 7 by 512 tensor. We flatten it, and then we pass it through a sequence of feed-forward layers in order to get the object recognition output. It is trained to do this already. Next, what we do is we make the modifications in order to get the fast RCNN structure. This is like what we mentioned before, right? So we have like 4 convolution activation poolings, followed by convolution activation. And then remember, the last max pooling, there was like a max pooling over here. We're going to replace that with RoI pooling. So we add that RoI pooling layer. And then what we do is we replace also the output 1000 neuron layer with sibling layers for classification and localization. And hence we have the fast RCNN architecture, which is not fine-tuned. Next, what we do is we get training data. So this is the data with bounding boxes, which can be used to fine-tune the network. So for example, in this image, we have like, localizations and classifications of dogs. We also have a leaf over here. These are like other dogs, and so on. We'll have like many of these. Now what we do is we'll take one of the training images, we'll pass it through a region proposal algorithm to generate 2000 region proposals where an object may be present. Of these, we're going to select 64 of them. And now the way that we select these 64 is such that 25% of them will be our positive labels and 75% will be our negative labels. And with the 25%, they will have an IOU of the ground truth bounding box and the foreground class region proposal, like bounding box, that will have an intersection over union of greater than or equal to 0.5. So this means that if like a region proposal is overlapping with our ground truth bounding box for some like dog, then that region proposal kind of largely represents a dog, and hence we will mark it as a positive label. And this is for like 16 of them, or 25% of these cases. Now, for the other 75%, which is like 48 region proposals that we randomly select, if in this case, like the intersection over union of the region proposal and the ground truth label bounding box, they should have an intersection over union of, between 0.1 and 0.5. And this means that these region proposals might consist of some amount of like a dog or some amount of a leaf. And those are the ones that we are going to use as a hard negative label. And the reason we do this is because, we could have used a region proposal that's somewhere like over here, and the intersection over union with like a ground truth bounding box would be 0. This could also be a negative label, but what we want to do is make it very difficult and very tricky for the network to actually discriminate and learn something very important about discriminating, the dogs from non-dogs or leaves from non-leaves. And hence, these are known as hard negatives. That's why we use some value that's not 0 and between 0.1 and 0.5, just to make sure that the data set that we create is going to be somewhat discriminative and higher quality. And hence, from a single image, we now have 16 positive classes and 48 negative classes. And now what we can do is we can now feed the original image into our Fast RCNN network, where it's going to go through a convolution activation pooling sequence until it reaches, it becomes this 14 cross 14 cross 512 tensor, some representation of the original input image signal. And then what we can do is for each region proposal, we are going to execute this part over here. So let's say that we consider this green one. The green is going to be represented by the positive class and the red is the negative class. So let's say this region proposal is one of the 64 is over here. We can map this from the image space onto the feature map space. And so they're roughly the same region. So it'll be like somewhere right over here. Now what we do is, this representation, if this is like 14 by 14, you can imagine that this this bounding box of the region proposal might be like 9 by 4, right? And what we do from here is this is like some 9 by 4. Remember, we need to use RoI pooling in order to make this some fixed size tensor of 7 cross 7. So we perform RoI pooling, we flatten it, we get and then we can pipe this into the sibling heads of 1001 neurons here and 4000 neurons here. And what we end up with is, well, for the classification case, like the neurons, we might get, let's say, dog, that neuron outputs like a 0.7, leaf 0.01, cat 0.11, background, I put it as BG here, which is 0.2. Now for this other localization heads, we have 4 neurons that are for each object category. And this would be some function essentially of what we need to construct the bounding box. So you can imagine 150 and 100 are let's say the X and Y coordinates of the top left corner of the bounding box. This third one is 70, which could be the height of the bounding box. And then this other 70 is the width of the bounding box. And right now, we can also, we'll get some predictions for each and every single one of these object categories. Now, what we'll also have during this training phase is a label. So we have this image originally was that of a dog. And the coordinates of the actual bounding box is, it can be summarized in these 4 numbers here, where it would be 140 x 90. That would be the pixel point of the top left corner. It's of height 80 and width 80, right? Now, you might be wondering, why do we have this? Why are we actually making a prediction of the bounding box here? Well, recall here that, remember, during this entire phase, we are generating region proposals. So we have a region proposal. We know the coordinates here of the region proposal, but they are not the exact coordinates of the object itself. They have a high overlap, that's what we know, but this might not be the exact coordinates of the object. And the exact coordinates of the bounding box of the foreground class is given by this label. So this will help the network, eventually train and nudge these parameters in the direction of this actual label when it is here right now. So that's kind of why we have this label, or this is why we're also outputting the localization, in case that wasn't really clear before. So we have now a prediction from the model. We also have the ground truth. That means now we have the components to compute losses. So there's 2 kinds of loss that we use here. So for the first one, we are going to use, your typical classification cross-entropy loss. So you can imagine that this will be the negative log of the true label, which is negative log 0.7, and hence we get 0.356. And similarly, we're going to use something called a smooth L1 loss for this localization case, where we're going to compare, for this label, we have this label over here. We're going to compare these sets of 4 numbers and the ones that are predicted for this class, that is the dog set of 4 numbers. And if you do this smooth L1 loss, this is going to be akin to, the closer these boxes are in overlapping with each other, the lower is the loss. And if you run it with PyTorch, you're going to see, if you run it with this, smooth L1 loss, I kind of just ran it with these numbers. This is the formulation over here. And if you do something like this in PyTorch, you'll run it and you'll get 9.5. Essentially, it's going to be a number from 0 to a positive infinity, effectively, kind of like your mean squared error. And so you can kind of see it now zoomed out all in this one slide over here where we compute the losses. Now, similarly, we'll take another for the same image. We're just taking a different region proposal. Let's say it's that this, over here, it was a little leaf over here. So let's take this region proposal. We will now pass it into RoI pooling. Now, let's say this leaf is when we map it to the feature map space, you get a 7 cross 2. And we're going to map this to 7 cross 7. flatten it, make predictions, and the predictions look like this now. And here we say the prediction is 0.78. The label is a leaf. And the loss, if you do a cross entropy loss, which is like negative log like 0.78 or something, you might get like a 0.248 as your cross entropy loss. Similarly, what we're going to see is the prediction of leaf over here. Let's take a look at these 4 numbers that represent the bounding box of the predicted leaf. The label here is going to be 0 to 60, 27, right? This is the true coordinates of the bounding box that we have in our training set. And from the label and prediction, you can compute a smooth L1 loss. And now let's say that we take this other one. This time it's red, so it's a negative label. That means it just represents like our background of sorts. We'll project it onto the feature map space. We'll get, now this will be, let's say it's 6 cross 3 cross 512, so it's a different size tensor. We then reshape it to be 7 cross 7, and then we flatten it, get the predictions over here. In this case, the background is going to be, let's say, 0.64. And the background is labeled, and hence the loss will be like let's say 0.446. It's like a negative log 0.64. And when we're trying to compute though for the loss for the localization, we actually don't have the label for this, right? The bounding boxes are really only for the object categories. And because we don't have a label for it, we're just going to call the loss here as being 0. And so what we'll do now is we're going to compute this for each of the 64 bounding boxes. We can compute the losses, right? So once the 2 losses for each of the 64 region proposals are computed, we can then aggregate them to create a single weighted loss. And the way that we would do it is, we would take the sum of all the classification losses. There's like 64 of those numbers for this image. Plus, what we'll do is for every single one of those localization losses, we are going to apply some, this hyperparameter weighting. And this can be like, 0.1, 0.01, whatever it is. And this is kind of required because you see the scale of these losses are quite different, right? The scale of this localization loss is much higher. And in order to prevent this from getting, too much weight, when, updating the weights of the network, we can scale it down using this W hyperparameter over here. And hence, we compute the loss. And I've kind of also just written this as like a kind of like one of these flow diagrams of operations where, we take the prediction over here. This prediction, along with the label, is piped into like this cross entropy loss function to give a classification loss. Similarly, this prediction, along with the label for the bounding box, is piped into this, smooth L1 loss to give us the localization loss. And then we can use both the classification and localization loss into a loss aggregation function, which looks exactly like this, essentially, in order to get the final loss. And now that we have a final loss, what we can do is, we can perform backpropagation to update all the weights in the network until this point. So we repeat this procedure then for all training examples to get a fine-tuned Fast RCNN. And now what we can do is, here's the fun part for inference. We can take an image. We will then generate region proposals, like 2,000 region proposals over here. We will pass it through our fine-tuned network to get a 14 cross 14 cross 512 tensor that represents the image. And then what we'll do is for each region proposal, let's just say that we'll take like one region proposal over here. We would have mapped it from the image space to the pixel space. This is going to be like a 9 cross 4 cross 512. We'll map through a 7 cross 7 cross 512. And then we will be able to make predictions. Let's say that, for this prediction, the classification prediction of the dog is the highest. It's 0.85. And the corresponding localization is given by these 4 numbers, which we can use to draw a bounding box. And hence, what we do is we draw a bounding box, and we label it as dog with the classification score of 0.85. And this is the prediction for a single region proposal. And we now repeat this for all 2,000 region proposals. And in doing so, you're going to get something that looks like this. For 2,000 proposals, you have like 2,000 of these bounding boxes, which have like the object as well as the score for each case. Next, what we do is perform something called non-maximum suppression. Essentially, for every single foreground class, we'll sort the bounding boxes in descending order and remove the boxes that overlap over a certain threshold. So for example, in this case, let's just consider dog, right? So for dog, the biggest one is this 0.85. That's the highest score. So we keep that because it doesn't overlap with anything. Next highest score is this 0.72. It has a large overlap over let's say it's over some chosen threshold that we choose appropriately. And then that means that, well, if it's a huge overlap, we exclude the bounding box. Same with next 0.51. A large overlap at 0.85, exclude it. 0.4, large overlap, exclude it. 0.34, large overlap, exclude it. And so what you'll do is, ideally if you do this for every positive foreground object category, you're going to end up with a single bounding box that has a circumference around an object. And hopefully that will be the ideal object localization as well as classification. And so I hope this entire pipeline of using Fast RCNN for object detection makes sense. Now, what was wrong with RCNN, I hope it's also clear how Fast RCNN can help. So before we were complaining that object detection is a multi-stage process, and so it increases complexity, and also we require disk space to store those features for training. But now this is solved with Fast RCNN. We reduce the number of stages in the pipeline, and there is now no need to store the features that are extracted from an image during training and inference. Next is there's slow inference because of non-shared expensive convolution operations for region proposals, right? This was because for each region proposal, we had warped it and passed it into the Alexan architecture for RCNN. But with Fast RCNN, we only make that entire prediction on the original image once. So the complex, large convolution activation pooling operations happen only once per image. But it's only those smaller operations with RoI pooling that happen, 2,000 times, right? So it's much more efficient that way. And the third of performance loss due to distorted region proposals, well, because of RoI pooling, we no longer need to distort the region proposals in order to get their predictions. Instead, RoI pooling will help map those different sized region proposals to a fixed size tensor that can eventually be used in, determining, the classification and localization of the object. So I hope all of this makes sense. Quiz time. It's that time of video. Have you been paying attention? Let's quiz you to find out. Why does the Fast RCNN use RoI pooling? A, to convert variable-sized regions of interest to fixed-size feature maps for the FC head. B, to generate region proposals from the image. C, to perform non-maximum suppression on detections. Or D, to upsample small objects to higher resolution. I'll give you a few seconds to answer this question. The correct option is A. But did you get it right? Please comment your reasoning down in the comments below and let's have a discussion. And if you think I do deserve it, please do consider giving this video a like because it will help me out a lot. That's going to do it for quiz time, but before we go, let's generate a summary. In this video, we took a look at Fast RCNN, the what, the why, and the how. We started with outlining what RCNN is in its three-stage pipeline. We then took a look at what was potentially wrong with RCNN, specifically it being a multi-stage architecture which can take a lot of disk space for training, its slow inference because of, expensive convolution operations for every region proposal, and then its potential performance loss due to distorted region proposals too. And we saw how Fast RCNN can address these. So Fast RCNN uses a pre-trained VGGNet as its base, and then it makes two major modifications. The first is that it replaces the last max pooling layer with an RoI pooling, and the second is that it replaces the original classification 1000 neurons with sibling heads for classification and localization. This can then be fine-tuned on our object detection dataset for each region proposal as well. We also looked at how we can compute a single loss using the classification and localization losses, and hence backpropagate through this entire network so that this end-to-end network actually learns. And once we now have this fine-tuned Fast RCNN, we can then use it for inference. And so I hope that this entire process now makes a lot of sense. And we also saw definitively how Fast RCNN can solve each of the problems that we discussed with the original RCNN architecture. It no longer needs to store these large features for training. Inference is now faster as we now only do one prediction through the entire more expensive convolution activation and pooling. And performance loss is now not as much because we are not distorting these region proposals. And RoI pooling kind of here comes to the rescue as it can resize these random sized region proposals to a fixed size tensor to be processed. And that's all that we have for today. I hope all of this makes sense. I'll link down below a lot of the other supplementary resources that I mentioned before, specifically on what are region proposals and the original RCNN architecture that I highly recommend you also watch. And I'll also link down some papers for performance down below too. That's all we got for today. Thank you all so much for watching, and I will see you in the next one. Bye-bye.